In this video, we are going to go over the two proportion inference in SAS. And this program that I have on the screen here, I wrote in order to accurately display the hypothesis test and confidence interval for this, since there's unfortunately, at least from my research of it, no direct way to do it nicely. So I have here the whole where you type in all of the data in. Well, I shouldn't say the data. This is where you type in the various values. So we have alpha as a decimal, the first sample size, the first number of successes, second sample size, second number of successes. I have the confidence, the percentage for the confidence interval, and then the last one is the side for the hypothesis statements. So this is where the alternative hypothesis is L for a left-tailed test, U for a right-tailed test, or 2 for a two-tailed test, respectively. And all of them have the percentage in front of it, percent let each of these equal these values, due to the fact of when we keep calling it throughout the program here, we could use it in various functions and procedures, although we're just using it in the DAS step in this particular example. Then we name the data. In this case, I'm just calling it proportion. P1 hat would take the number of successes, event 1, divided by the sample size n1. The variance 1 takes P1 hat times 1 minus P1 hat divided by the sample size for the first sample. Then P2 hat takes the number of successes for the second event divided by the sample size for the second event. And the variance of the second variance is the P2 hat times 1 minus P2 hat divided by the sample size of the second sample. The difference subtracts the two P hats. It does P1 hat minus P2 hat, so be careful when actually noting which one is which. And then the P1 hat, which is supposed to be P bar, this takes event 1 and event 2, adds them together, divides by their combined sample size, so n1 plus n2. The variance for P bar takes that P hat, which again could be known as P bar, times 1 minus P hat times 1 divided by the first sample size plus 1 divided by the second sample size. The standard error for this is the square root of P bar, and Z here is the difference divided by the standard error to get the Z score. The critical value for this takes the quantile of normal, comma, 1 plus the confidence interval divided by 2. This is to find the critical value corresponding to that confidence level. Then 0, 1, since this is a standard normal distribution. The left side of the confidence interval is the difference minus the critical value times the square root of variable 1 plus variable 2. Variance 1 plus variance 2. The right confidence interval limit is the difference plus the critical value times the square root of variance 1 plus variance 2. And then we just named the left and the right limits as left bound and right bound. And then side we equal to the side variable that we had up here. Then if that side is equal to L, then we do p-value of CDF of normal, comma Z. This Z being the Z that we have up here. Else, if the side is equal to U, then we are doing then p-value is equal to SDF of normal, comma Z. And the SDF is used as opposed to CDF due to the fact that it's on the right hand side as opposed to the left. and then else if SAT is equal to 2, then p-value is equal to 2 times 1 minus the CDF of normal, comma, the absolute value of z. Then we just format the numbers, so that way we could determine which one's which. We drop the 2 variances, and then we run. And then the bottom here we have procedure data, print data is equal to proportion, and then label noobs, and then run. So let's say, for example, I want alpha of 5%. Then sample size, let's do a first sample size of 1,000. Number of successes of, let's say, 950. Sample size for the second, let's also do 1,000, but this time do a number of successes of 900. And we're going to do a confidence level of 0.95. And let us do for the side here, let me first erase all this. The side for this, let me use a not equal to, so a 2. Since naturally these are not equal, right? We have a 950 and 900. Event 1 should be bigger than event 2. And then we're going to run this. And as you can see, it gives us a whole bunch of this information here. We have the bounds. So the true population proportion will be between 0.02 and 0.07. The difference between them, I should say. The difference between the two samples is 0.05. But the true difference is supposed to be between 0.03, actually, about, to 0.07. And we have a probability value here of less than 0.0001. That just meaning that we have evidence then to say that these are not equal to each other, which they are not, as we can tell by the fact that I used 2 totally different numbers. Let me know if you have any questions or concerns. Thank you.